So let me tell you about sort of the mode that people are working in nuclear theory, working with, for example, the Oak Ridge group. They are taking advantage of, it was mentioned there are these cloud computing quantum computers like the IBM QX5 on 16 qubits. There's also the Rigetti on 19 qubits. And so these have been used in a couple of recent papers. One of the papers, let's say, there was the paper by the Oak Ridge group where they did a calculation of the deuteron. It was the first quantum computing calculation for nuclear physics, I guess, where they took interactions between the proton and neutron to be very simple, some zero angular momentum interaction, or S-wave interaction, and they did a calculation using this variational eigensolver technique. Basically, you calculate matrix elements of the Hamiltonian for different variational states. So these variational states, they cooked up just by tuning some knobs in the unitary evolution of the state. And they were actually able to do a good job, but to be honest with you, it is a very simple problem. But I'll also tell you about some of the problems that you face, and this is the main problem, the fidelity issue, right? So if you have a single qubit gate, it's pretty good, right? So you see the fidelity for the IBM and the Rigetti are at the level of, well, the IBM's better at 99.7 or so. But the problem is the 2 qubit gate fidelities are rather low, and so you can't do too many of those guys. And that's where you get problems. Now the readout is just a final step, so that's not such an issue. But it's really the 2 qubit gate fidelities that you have to run up against. Another calculation that has been done was by the Institute for Nuclear Theory folks, in particular Martin Savage, who's in the Institute for Nuclear Theory, and his postdoc, Natalie Klecko. Oh, by the way, I should mention one thing about quantum computing is apparently it pays very well. Because in nuclear physics, the postdocs get, typical postdoc salaries. I've been told that this fellowship by Microsoft pays $130,000. So anyway, she's the lead author on this paper, and they did a simulation of 1 plus 1, that's a time dimension, obviously, and one spatial dimension of the Schwinger model, but because, okay, I should explain what this Schwinger model is. The Schwinger model is quantum electrodynamics. It's basically QED. It's electrons with the interaction mediated by the exchange of photons. And so they study this in one spatial dimension, but because of the limitations of the number of 2 qubit gates they can use, they simply took 2 spatial sites. So it's basically a 2-site lattice system with periodic boundary conditions. And so here's sort of the setup. The reason there's 4 sites here is they use a formulation that's called staggered fermion formulation, where they double the number of sites to take care of the different spin states, or actually the electron and the positrons. And so they were doing a few things. One of the things they did was to find the ground state of the system by this variational method. But the other thing they also did was take a look at the time evolution of the system, the real-time evolution of the system. They could do it because they used a lot of the symmetries. They reduced the problem to essentially a 4-dimensional matrix, if you want. And then, so you can then store it onto 2 qubits, and then any unitary transformation, any unitary matrix can be written down in terms of a couple C0 gates and single qubit gates. And so that's how they were able to do these simulations, and they got the real-time oscillations that they read out, and it worked quite well. So that's kind of exciting. But the real challenge is to go to real-time evolution for larger systems where you can't just simply say it's a 4x4 matrix and we can cheat by using this little transformation. What you really want to do is something called Trotter breakup. That is, you want to do little time evolution. So the problem is you want to solve a many-body system where you have lots of degrees of freedom, and there are interactions between these pairs and these pairs here, and you have operators that don't commute with each other, but you want to do the exponential of minus ht of that guy. And so the Hamiltonian, the h that I said, has operators that don't commute. So the way you do that is by breaking up the time into small pieces and doing small time evolutions. So what you really want to do is to do small time evolutions where then you could take just one 2 qubit gate and do the exponential, actually to do the unitary transformation there, and then go on to the next gate, right, in little time steps. The problem is you need to do a lot of gates there, and that's where the fidelity issue comes to be a problem. I'm not really sure how we'll solve this problem, because I'm going to go to Oak Ridge and they'll ask me what problem I want to do, and I'll say I want to do real-time dynamics too, and then we'll have the same issue. I believe, if I'm going to guess into the future, and I'm not really an expert in the field, I believe one has to take advantage more of sort of the natural quantum system that you're working with in order to beat this problem. Probably something more along the lines of something in between a quantum computer and a quantum simulator. There might be some sort of default mode in which the system's completely coupled, in which it will have its natural time evolution. And probably something in between those two may be a way to solve the problem. In other words, we kind of have to deal with the quantum system that we're working with, and maybe the universal quantum computer for a real problem that we really want to solve may be a little bit far away in time. Okay? That's all I wanted to say. Thank you.